That means doing calculation. This is actually why you are mainly here. Not only because there comes something else, but this is why you are mainly here, doing really computational science based on, for example, density function theory, but also something which is beyond the traditional density function theory and what is really based on molecular dynamics. This has been really an extremely efficient and extremely popular field. What we see now since a couple of years, or you can actually say even just happening on these days, is what I call big data driven science. I think it's really an independent fourth paradigm how to create knowledge, something completely new in saying we do not really start with a law or with a model, at least as little as possible. We start with data. And we look at the data and we look and find structure in data, and only after we have seen patterns and structure in data, we think about what is the reason of these patterns, and from that we then actually get for new insight. This is the detection of patterns and anomalies in big data. Machine learning or other actually tools are behind this. This is, I feel, is something coming up right now, and we will talk a little bit about this in the second week of this lecture, and there will be also actually a tutorial on this. So, in fact, this big data issue is a center, and you will talk to many people from this, is at the center of the interest in what is called the NOMAD laboratory, where NOMAD stands for Novel Materials Discovery. This is actually what is now the largest repository of input and output files for all computational material science computer codes. So many things you probably like to do, you don't have to do anymore because actually it's already there and you can look it up that these calculations have been performed already. But NOMAD is not only really having a repository of input and output files, it also in fact offers really big data services. Realizing that big data is really, if you look into structure and patterns, a new way to get scientific information. And I want to show you this in a 3-minute YouTube movie which we created, which you find here on YouTube, but actually as this talk was actually half of the talk was given just in China, and in China YouTube is banned, so we also put this on UQ, so you can actually see it everywhere on the world. And so let us actually have a look at this, and actually I have to see that really the things work properly, so hopefully it works.
The NOMAD European Centre of Excellence, your gateway to material science data. This is John, an engineer in the sustainable energy field who wants to build the best solar cells ever. And this is Laura, a chemistry researcher who wants to design the most efficient batteries for the next generation of electric cars. So what do John and Laura have in common? Well, to achieve their objectives, they both need to use new high-performance materials. So what can material science do for them? The ideal solution would be to provide them with a map of materials where they can identify and select what they need. Indeed, the amount of different possible materials is practically infinite. So what if all materials could be grouped according to their properties and functions? Is this already possible?
Oops. Come on.
This is the idea behind NOMAD, the Novel Materials Discovery Laboratory. NOMAD is the European Centre of Excellence for Material Science Data, set up in 2015 to enable the quest for new and novel materials and their properties, and to reveal unknown properties of already known materials. The foundation of this European Centre of Excellence is the database called the NOMAD repository, which is available to all and based on open access principles. It hosts input and output files of all significant computational material science codes for at least 10 years, for free. It also enables a confirmatory analysis of materials data, their reuse and repurposing. As the NOMAD repository includes extremely heterogeneous data, which do not allow for direct comparison, these are being processed into code-independent, machine-readable, and standardized form. This is the NOMAD archive, which provides the open access data from the repository in an easy-to-use and easy-to-access way. The archive is the base for the NOMAD encyclopedia, which displays the properties of computed materials based on millions of calculations, that have been performed worldwide. Not only does the encyclopedia provide information about known compounds and their known properties, but it also makes it possible to propose a previously unknown material with the desired characteristics for a special application, or to bring to light the previously unknown properties of known materials. The Nomad COE also provides a set of big data analytics tools that uncover structure and correlations in big data of materials. This enables scientists and engineers to decide which materials are useful for specific applications, or which new materials should be the focus of future studies. As seeing helps understanding, Nomad is also developing a virtual reality environment to allow for interactive data exploration, training, and dissemination. Clearly, all of this is made possible by the underlying Nomad high-performance computing platform, which consists of a distributed multi-layered storage system connected to scalable computing capacity. Data is the raw material of the 21st century. If you deal with material science, the Nomad Centre of Excellence is your gateway. Start using it now at nomad-coe.eu.
Okay, so this was a very basic or simple way to really summarize what we have in mind with this Nomad activity, which, as I somewhat said, is, I think, really entering the next phase, or actually the next paradigm of how to really assemble knowledge. So in some simple ways, again, what will we discuss here, but actually will be mainly discussed also next week, these different components of Nomad, which you have seen. In fact, just to give you an idea about where we start with, and so Nomad is used really by many people on this planet, or actually in the solar system already, and many things are there, but in fact, if you really look into this, many things are not there. So far, if you talk about total energy calculations, which is what we are doing during the next 10 days, there are already actually 39 million calculations on this, which sounds big, but on the other hand, material science is such a big thing. Actually, it's still not really sufficient for many things, but for many things it is. What we will not really discuss very much is visualization, but you actually got some VR glass in your conference material. So if you have actually time, there are two movies which you may actually like to look at some point. One is carbon dioxide activation, trying to understand what you can do with carbon dioxide. It's not really a bad gas. In fact, if you know actually what you can do, CO2 could be actually a very good raw material for new fuels. So there's no reason really to put everything in the air and to create global warming. You can actually also use CO2, and one way to use it is catalysis. And another movie is actually the exciton in lithium fluoride. To show this, that's something which you cannot really look usually, because it's, the exciton is an electron hole pair. This has 6 coordinates, the x, y, z of the electron and of the hole. But what you can do is actually put yourself in the hole concept and look actually where the electron is, and this is what you can do with your virtual reality. So if you're not really, one thing is very important: as soon as you have opened, you have to really press this thing, because otherwise if you don't really activate the virtual reality, you don't really see this. Now you may actually use this with your VR glasses, but we also have actually a Vive system installed here at the Humboldt University. And that is actually then a real one, because with the glasses which you have and with your smartphone, you can actually look around. Actually, if you use it, you will see that something happens behind you, and then so you have to turn and look around. In the true virtual reality, you actually also can walk ahead or jump or actually fall, and so that you can also look at that in this Vive system here at the Humboldt University. But that only actually you can do one person at the same time. So just if you have time, just really ask Pasquale or ask Claudia Draxel. Here we have actually the Nomad archive, the number of calculations as a function of different codes, where in fact we only list here the codes which have actually more than 100 uploads. And so you see actually codes like, which you know probably CASTEP or CP2K, or actually exciting, FHI Ames, Gaussian, GPOR, Quantum Espresso, WASP, and Wien2K. WASP is really the leading. So actually this is very important, this is a logarithmic scale. So WASP is somewhat above 10 to the 7. That means actually more than 10 million. The next one then actually is FHR Ames, which is below actually 10 to the 7. WASP is so big because the biggest databases in America are run by Stefano Cottarolo, which is aflowlib, and then another one is run by Chris Wolferton. These two are actually part of this NOMAD activity. And so if you want really, this is actually nice that for example, in Chris Wolferton's thing, you can only, in this database, you can only look at results. But if you want to see what the people have really done, if you want to look at the input and output file, you have to go to NOMAD. And so basically all the big guys are also a part of these activities here. I should say, actually, Stefano Cottarolo is right now in Berlin, staying for a year, and so he will most likely come to this excursion to the Teufelsberg. So if you have questions to Stefano, you actually have to use the excursion day to talk with him about aflowlib. So with 30 million or 39 million total energy calculations, and every calculation, of course, provides a lot of different results, geometries, energies, and then other details. We really are facing what is called the big data challenge. Talking to people from computer science, you really see there are significant difficulties you have to deal with. And as you want to enter this field, doing DFT calculations, but you will then also see, depending on what you want to do earlier or later, that you really want to do high throughput calculations, you will actually see there are several challenges you have to deal with. One is the volume of data which you create. The other thing is the variety, which in fact in computer science means the heterogeneity and the form and the meaning of data. This is a big issue, or has been a big issue for us, because if you have seen, there are so many different codes which have been developed in chemistry, in physics, in material science. They all speak somewhat a slightly different language. They have different energies, they have different energy zeros. Sometimes they all call it something an energy, but actually one means actually a different thing than the other one means. So really making a conversion, from the original data to this code independent thing, to make really, to fight this variety, was a big effort to do, but this we have done. So now actually we are actually happy with this. Velocity at which data may change or new data arrive is not really a big problem, because our calculations usually take several thousand CPU hours, and so actually that's not really coming in too many things at the same time. Veracity is another thing. So veracity is what really computer science calls the uncertainty or the quality of data. We usually call this in our field verification and validation. This again will be part of these lectures. I think Stefan Coutinier in particular will address this. I think also Volker Blum will a little bit address this. This is something you want to know, in fact, what is the accuracy of your calculations. And some calculation may be good for some quantity, but actually with this basis set maybe not good enough for another quantity. Understanding this is a key issue. The main issue in NOMAD, at least, and I think at some point also in your work, will be what to do with the data. So far, when people do calculations, they have a specific question in mind. They want to understand, maybe is this, say, semiconductor a good option for some photovoltaic, or is this material a good catalyst? But in principle, you can actually use these things also for other things. Titanium dioxide you can use actually for understanding why is your toothpaste white, or your sun cream, or what the color, or why is it actually a good Grätzel, or say a photovoltaic cell, or is it a good support material for catalysis? All these materials are really used for many, many other systems. And so far what people have done, they put everything on a hard disk. I'm saying actually it's like putting the elements of a jigsaw puzzle, just throwing them on the table, but not trying to put it together. Just really let the computer look. If you look for a certain puzzle piece, you just look at all the pieces individually. This is done usually when people do high throughput screening, but more and more in this fourth paradigm, I think we try really to find structure in this data. And as I said, material science data is not really just really data, but there is structure, and finding the structure is one of the issues we really want to do when you do the next step in material science. The main issue, as I said, actually volume is not, but variety is one, but this is one which we have solved. Veracity is something which I said also we will address. And coming to the veracity or the accuracy, again, Nomad is offering, and you will briefly discuss that also in one of the tutorial, is offering a tool which tells you about the accuracy. Using the 4 most different computer codes, using basis sets like plane waves, using basic like grids, using say LAPWs or our say atom-centered numerical orbitals, having a certain type of setting of K-space and basis set, you can with this tool really get an idea what is the accuracy for a certain question you have. So this is actually what I wanted to say about this 4th paradigm and really going to big data, which I think is the way how things will evolve in the next next years. But now actually they become really to the main issues also, which is a little bit of the structure of our hands-on workshop here. If we want to understand material science or materials properties better, we want a predictive modeling or simulation. This means we must address all time and space scales. So just doing really something which is, say, on one scale doesn't really not really help and give you much insight. So if this is really space or length and this is time in seconds or hours, electronic structure theory in the standard way somewhat gives you some ideas about the femtosecond time scale. Very important for many things in basic science, also very important in many things for maybe for some modern technology. But if you go on, if you really think life is not static, life is dynamic, you have to couple it to molecular dynamics, which then is called ab initio molecular dynamics. That brings us to something like nanoseconds, which still is actually not very long. What is the length scale we really need? If we make contact to things what people in engineering are interested in, you have to go to minutes or hours or maybe even years. So just one example, if you want to understand corrosion. Corrosion happens in 1 atomic layer per minute. So if you do something on the femtoseconds, you will not have a 1 atomic layer per minute idea. So you have to go to longer distances or longer time scales. And that means, in fact, you have to couple molecular dynamics with mass equation and kinetic Monte Carlo. Again, there will be talks in the second week which will address that. And if you really want to go for beyond, say, several hours, you have to link this in a way to continuum equations, to rate equation and finite element modeling. This is all what is necessary, so things are not anymore just in running a DFT calculation. You have to really think what to do with these calculations. And I give you a little bit of an introduction, but you will see more during these lectures. So this is in fact where we want to be, right? If you really want to make contact with real life, this is where we want to be on a time scale of seconds, hours, maybe even years. This is where we want to understand how a material really behaves. Of course, everything is built on a base. The base is electronic structure theory. If your base is bad or rotten, everything you build on this rotten base will fall apart. So one thing is very important, and this is why in the first week we really put a lot of emphasis on this, understanding the accuracy of the calculation. If you have understood that, and if you make sure that the accuracy is not lost in going up, then in fact you're doing a good job. But obviously we need, in going from one simulation to the next, to the next, to the next, we need robust error-controlled links with knowledge of how bad are we doing, or uncertainty between the various simulation methodologies. And again, I hope that you will see actually how we can do, and I think we're doing pretty well up to the green thing. From the green to the blue, there's still a lot of basic science necessary to be developed. So in the first couple of days, we talk about electronic structure theory, about density function theory, and beyond. This starts from the many-body Schrödinger equation. We want to do electronic structure theory, and DFT is just one approach to do this. It's the most efficient one, and I say some words in a second. But there is, of course, the equation which describes everything. The many-body Schrödinger equation, which has the kinetic energy of the electrons as an operator, the kinetic energy either of the nuclei, or if you want to take core electrons and nuclei together, you would say of the ions. You have the electron-electron interaction, electron-ion interaction, and the ion-ion interaction. This thing times psi equals E times psi, where psi is a complex, very complex beast. So if you have materials, you have 10 to the 23 electrons, and also somehow 10 to the 23 atoms. So that means you have something with 10 to the 3 coordinates. Nearly impossible to handle in general. The operators we know, right? It's just really the momentum operator divided by 2m electron mass, or momentum operator by 2m nuclear mass. Electron-electron interaction is mainly the Coulomb interaction between electrons. Ions is also Coulomb interaction, and the electron-ion is actually also Coulomb interaction of an electron in the electrostatic field of an ion. So the operator is 100% known. There is no open question. We know the Schrödinger equation exactly. So what is the problem? Now the interesting thing is the problem has been stated already in 1929, and we are still actually completely supporting what Dirac has worded in 29. The underlying physical laws necessary for the mathematical theory of large part of physics and the whole of chemistry are thus completely known. This is this Hamiltonian which we have just said. And the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble. Typically when people quote Dirac, they stop here. But I think actually what it continues is what this workshop is all about. It is therefore becomes desirable that approximate practical methods for applying quantum mechanics should be developed. They should be approximate and they should be practical. This leads to an explanation which can lead to an explanation of the main features of complex atomic systems without too much computation. Now this is something you could argue nowadays, but I think this is the thing. There's no way to do an exact calculation. We need approximations, and we need to understand the quality of these approximations. So everything is known, and what is the complication? The reason of the complication is electron-electron interaction. This simple operator makes it so difficult to solve the whole thing, and so most calculations really, or actually nearly all calculations actually deal with an approximation to dealing with this. Still, we start with another approximation, which doesn't really help in this regard, but which is also very important and typically simply assumed without more thinking. And I think this is very important also for future new work to think over. Why do we accept that? And in fact, we should not at some point. This is the Born-Oppenheimer approximation. We see that the wave function depends on electron coordinates and on nuclear coordinates. What we can do in general, we can write this down as a linear combination of wave functions which come from what we call the electronic Hamiltonian. HE is just a part of the Hamiltonian which has the electron coordinates in it. So we use actually the solutions of HE as a basis set if you want, and we sum over all these functions with some coordinates, which then of course, with some coefficients, which depend on the nuclear coordinates only. This is still exact. This is not an approximation. The Born-Oppenheimer approximation says we start from that, but now we really neglect everything which has a factor electron mass divided by nuclear mass in front, arguing that this ratio is, say, 1 over 1,000 or 1 over 10,000. True, it is this of this very small quality, but it goes together with the matrix element. And the matrix element actually can change the picture completely. And at the end it means in this summation we only take the lambda 0 term, so we don't really summation, we just have lambda 0 times this wave function. It means that the dynamics of the electrons and nuclei decouple, means also that if nuclei move, electrons are always instantaneous in their electronic ground state. I say something about the quality of this in a moment. Actually, I always say it here. So some limits of the Born approximation is that if there is a correlation of the dynamics, that is not included. So superconductivity, which comes from electron-phonon or polaron-induced superconductivity, is not included. There are dynamical Jahn-Teller effects, that the fact that systems really distort because of a degenerate electronic state, which in fact sometimes yield to a dynamic system which are not really treated appropriately. Diffusion in solids, when nuclei move, they sometimes really on the transition state move faster than electrons can really follow. Temperature dependent band gaps, known adiabasity in the electron surface getting in chemical reaction. If a molecule scattered at the surface, very often because, for example, because of electron spin, it cannot really go to its ground state. Relaxation and transport and charge carriers, these are all questions which are still open and not been answered. And I think the more one looks into the experimental result, the more you see that there are problems with this approximation. Nevertheless, in this workshop, we will keep in mind, hopefully, that there are limits with the Born-Oppenheimer approximation, but we will use it. We will concentrate on the following really on this electronic Hamiltonian, kinetic energy of the Hamiltonian, electron-electron interaction, and electron-ion interaction. That brings us to the total energy, and there are actually the following terms one also should keep in mind. Very often it is not so important, but what is called the total energy in fact has several terms. It has this term which comes really from this Schrödinger equation which you just have seen, or this is the quantity, the ground state of the electrons, for example coming from density function theory. And we have to add to this to get a total energy the nuclear-nuclear interaction or the ion-ion interaction, which is just a classical electrostatic term. Very often this is called the total energy, although in principle actually there is another term, namely the quantum mechanical correction of lattice vibrations, which is the expectation value in this lambda 0 state which you have seen before of the ionic kinetic energy. This means that nuclei are never really just fixed, they always vibrate, even at t equals 0. And I plot this here in the following way. If you look at a typical curve, which we also will calculate in the next days, a typical curve going actually from interatomic distances which are large, and you're going actually to smaller and smaller one, you're going to a minimum, and then actually there is then behind the minimum, getting even closer, there's a very steep rise. This steep rising comes from a Pauli repulsion because electrons don't want to be compressed in their space, and this really is a smooth and somewhat softer function as on the left side. Looking at this magnified, we have a parabola-like figure, but actually it's only parabola-like in the sense that this is steeper than this side. And so if this is the minimum which we usually calculate, what people will measure is not this quantity. What people will measure is a little bit bigger, namely it's the average of the vibrations. There is a 0-point vibration, the system will vibrate as is indicated here, and the midpoint of this is a little bit bigger than what we calculate. You can say typically this is not important, it's a small correction, but there are several issues where it plays a role. And where it plays also a role in really renormalizing some electronic structure properties. Anyhow, we should keep this in mind when we compare with experiments, and in fact we really want to look into some electronic structure data which are, where details really matter. Now, how to deal with these things, and this is what density function theory is all about. A very schematic but actually correct description of density function theory of the Hohenberg and Kohn theorem. This was developed in '64. So this is a photo I took from Walter probably 4 or 5 years ago. And the idea is the following. If we have, say, the set of all functions, of all ground state wave functions, so this is just a thought experiment, everyone. So just assume we have all the wave functions which are possible from all thinkable n-particle Hamiltonians. Different Hamiltonians have different wave functions, and so that's why I plotted this way. And then we have another set of now electron densities. And again, ground state densities which belong to the ground state of all thinkable Hamiltonians. Going from the left to the right, we know from quantum mechanics. The density is a functional of the wave function, and this functional we know explicitly. If you give me the wave function in principle, I can calculate this expectation value by summing over these Dirac delta functions. So going from left to right, we know how to do this in principle. Every wave function has a density. And now there was this proof which goes in mathematical terms by this nice phrase, reductio ad absurdum, which means actually you start with an assumption and you use this assumption and the result is absurd. And if the result is absurd, then actually means your assumption was wrong. And that is actually how they showed this. They assumed that two different wave functions could give the same density. In this assumption and doing then some type of analysis with your Schrödinger equation, you see that this is actually giving a stupid result. And that means actually this is not possible. The dashed error is not possible, that there is a one-to-one correspondence. Every wave function has one density and only one density, and the densities are different. That means whenever I have a density, there's only one wave function. That means, in fact, the wave functions here, when I said actually I want to calculate energy, which I calculate with an expectation value of psi h e psi, I can really express all of this in terms of a density. The energy can be expressed as the energy functional of the density. I don't need, in principle at least, the wave function. In principle, I will modify this statement in a moment. At least for a tutorial thing and for a concept building, this is an extremely important aspect. It means that if you use a Schrödinger picture, you have an energy as a function of the wave function. So this is just schematically. So let's say it could be one axis. Of course, it cannot be one axis, where all thinkable ground state wave functions are listed. Everything depends on 10 to the 23 variables. There's only one ground state true wave function, and this is where this energy expectation value has its minimum. And that's actually how basically all methods go. You evaluate this expectation value and you look for the wave function which minimizes this expectation value. Density function theory says, yes, that is of course true, but there's another functional, which is the function of the density, and only at this minimum you have the right total, the correct ground state electron density. Now this is of course much simpler because now in principle this axis has only n of r, namely something which depends on 3 variables. So that was a fantastic concept which really stimulated a lot of thinking and further development. And again, Walter Kohn, together then with Lou Shem, went on and wrote down the energy functional in this explicit form. Somewhat guided by Hartree, or you can also say Hartree-Fock, they say, let's assume that the density can be written down in terms of a density of 3 known interacting electrons. That is an assumption, but actually it's very general. Every density which is thinkable can be very infinitesimally close approximated this. And that means actually let's use the kinetic energy of known interacting electrons. Then we have the interaction of the electrons with the nuclei. We have a Hartree part, so all these things are somewhat clear. And we have something which is not known, and that they call exchange and correlation. Again, a function of n. If you have done this, you can actually show that this is equivalent to a Schrödinger type of equation, the Kohn-Shem equation. The important thing is this. So Ts, kinetic energy of independent electrons, EXC is the unknown functional. And that again brings us to what Dirac has said. We need an approximate way, but it should be practical. And I've written this down here somewhat in a different way, but with the same message. The challenge is to find useful, approximate exchange correlation functionals. Of course, there is, or has been really the hope that there is actually a functional which is the truth. In fact, we now believe, in fact, there is no such functional. The existence of a one-to-one relationship, right, that the wave function determines the density or the density determines the wave function, does not mean that there is a simple analytic equation. It does not imply that the exchange function, correlation function can be written down as a closed mathematical expression. In fact, what we have is what I call an algorithm. It means the density, when you give it to me, determines the many-body Hamiltonian. If you look at the density, you somewhat know where the atoms are, and you look at the density, actually, you know also what the nuclei are. And the Hamiltonian then actually determines the energy and the wave function. So that the fact that there is actually, it is a function of the density, does not mean that we don't need to solve the many-body Hamiltonian or the many-body Schrödinger equation. It just means actually there is this clear relationship, but it goes via the Schrödinger equation. So having something which is an approximate analytic equation or formula is always an approximation. How to deal with this? Oh, okay. This is actually so Walter Kohn died about a year ago, and so this is from some obituary which I already given. Let me actually just say about the importance of density function theory. If you look at the number of papers which have actually the phrase density function theory in, you see actually how it really has changed over the years, increasing to something like 5,000 papers per year are in density function or dealing with density function theory. And what was really surprising in creating the graph, which is actually was created by science, is the blue curve. You cannot really have a patent which actually is based only on a theory, but in fact here you see that patents use as an additional argument a density function theory calculation. Something like 500 patents per year are using this. So you are in a very active field, and the Nobel Prize was given somewhat in this year, and now you see actually this is really an enormous increase. Now actually I just to say actually how to make a successful career. No, actually, I mean, I don't really want to say actually you should follow my route, but actually this is when I started. So when it was 0 here, it was actually not very high there. So if you really know, if you know actually there is actually something coming like this, you should start. Now, you never know, right? It could have been also a disaster, but actually it's a good thing really. I think starting here with density function theory is not very creative, right? But
should they leave now? Should they leave now?
They should actually go and look and go to actually a multi-scale and beyond type of methodologies. Anyhow, just actually, I also actually have here, which I thought I'd have taken this out. I have a nice symmetry type of picture about Walter Kohn. So Walter Kohn was born in Vienna, and here you see him at a theater play with his sister. So this is Walter, this is his sister, and he is playing a person called Professor Nichtwisser, means Professor Know Nothing. So this was actually 34 years before DFT invention, and this was actually 34 years after DFT. So this is Walter, and this is the King of Sweden. So actually, just I felt that the symmetry is nice in how things really change. Now, as you said, the important thing is to find a practical solution for the exchange correlation functional. Things have been extremely successful, and the way it's very often really written down is realizing that this unknown exchange correlation functional can be, this is still actually correct, written down as the exchange correlation functional per particle times the density and integrated over R. So this is correct. And in the spirit, now I'm simplifying a little bit, but in the spirit of a Taylor type of expansion, you can say, let's really say this thing should be said as something as the exchange part for a constant density, and then some corrections which depend on nabla of the density or nabla square of the density and so on. And this thing, EXC of a constant electron density, which then is called actually the exchange correlation energy per particle of gallium, and as n is constant, this is now a function. This has been studied even before density function theory. This has been studied even in the 1920s of the last century. And the interesting thing is, so for constant electron densities for gallium, if system is at least locally constant, you know the exact exchange correlation functional, at least. Wigner has shown this in 1938. So this is EXC of gallium as a function of density. This is the exact result for low densities, we knew this. And for high densities, Gell-Mann and Brückner have done this in 1957. Now all materials are here. And so the question is actually, what is here? And of course, as I said, actually we started actually with DFT before actually we knew what was there. But in fact, Scheffler and Alder did a quantum Monte Carlo calculation for this range in particular. And here comes the surprising result. So this is how the curve looks, very nicely and smooth. And so now we know at least numerical. So here we know analytical, here we know analytical, and here we know the numerical result from Scheffler and Alder, the full curve for gallium. This approximation, as you have known, this local density approximation is still used. It's still actually for many things actually a good thing, but of course we are also doing better. Approximate exchange correlation functions have been very successful, but there are problems. Van der Waals, and you will hear talk tomorrow by Kachenko, hydrogen bonding, certain covalent bonds, you will hear that, certain correlated systems, and for sure for excited states, which again several people will teach to you how to deal with this. But for many things, when you know what you are doing, actually you can do this approximation or other approximations. And the hero in other approximations is John Perdue. I call this John Perdue's dream. I mean, he calls this Jacob's ladder. In fact, it was really in this Old Testimony, in the Bible or whatever, this dream by Jacob that angels are really stepping up a ladder to heaven. And in this idea, he felt there is some ladder also in density function theory. I call this Perdue's dream. And the ladder somewhat is written down here. It really goes, at least in spirit, in terms of accuracy. Now, if you really remember what I said about this functional, that in principle the functional does not exist, you can in fact make it better in the sense that it fulfills more of the known sum rules and constraints which are there, but that does not necessarily, if the functional doesn't exist, it does not necessarily work always. But anyhow, the work goes from the local density, which we just have discussed, to the general gradient approximation. Then there is a meta-GGA where the most promising nowadays is called SCAN, which in fact is a meta-GGA. So meta-GGA means it has the gradient of the density, and it also includes the, say, second gradient, if you want, or the kinetic energy density. And SCAN fulfills 17 of the known constraints, all constraints which a meta-GGA can fulfill. Still, there are severe limitations of that. There are some constraints which it does not fulfill. But anyhow, this is somewhat the best on this level. Then, of course, it goes higher. Then, to some extent, you can say it removes a little bit of the beauty of density function theory. We now introduce or accept also wave functions of the Cohen-Chem equation. It does not destroy density function theory because the wave function is a function of the density. So you can actually use this information. This is B3-lib, PBE0, HSE. You will play with some of them. And then even higher, unoccupied state where you have exact exchange and correlations treated in the so-called random phase approximation as given by the adiabatic connection fluctuation dissipation theorem. I think Igor may talk a little bit about this. This is somehow our favorite, but when I say actually this is our favorite, one also has to say this is a factor of 1,000 or 10,000 more expensive than anything else, so you cannot really do calculation. You can make a test calculation with this, but you cannot really use this for production. John Perdue is the most cited physicist ever. So more cited than Schrödinger, Einstein, Heisenberg, and so on. Now, when he was giving a talk here some years ago, I was actually joking and saying, actually, yes, he's the most cited scientist. But actually, you get only famous if you're not cited anymore, if everything in the textbook is cited. Right? But actually, he's a fantastic scientist and a great person, so you can joke with him. So basically, the reason why he's cited is also that these methods are used in chemistry, and they cite this. What is bad with all the citation things and H factors is actually, that doesn't mean that people read that, right, or understand that. So I think you should really read the papers and not just cite them. Everything you cite, you should also read. And I think, but he's really one of the great heroes in this field. And you will see more about this in the talks to come. So the functionals of level 1 and 2, which is LDA and GGA, which are still the most popular ones. I would say actually probably 90% of all the calculations are done with the GGA type of calculation. They suffer from what is called the self-interaction error. you have seen that the total energy, or the total energy had in fact the Hartree term, and then comes the exchange correlation term in. In the Hartree term, you have the full electron density. That means you have include the electron which you want to calculate to some extent, or the Cohen-Shem quasi-particle, whatever you like to call this. That is not correct, and this, what is wrong there should be corrected in the exchange correlation function. It's not really done very well on level 1 and 2. All these functionals 1, 2, 3, and 4 are lacking long-range van der Waals tails. So if you deal with organic systems, if you talk with biosystems, and again you will discuss it in very much detail, you are somewhat lost. Alex Zachenko will talk about this tomorrow, I believe. Right? Anyhow, so we have now a way that we can look into validation, that we can look into some error estimations, but it comes really with an extremely cost. But in principle, since say very few years, we are actually at a level in material science that we can in principle go into this. Let me show you what I think is still very impressive, which are the first calculations in density function theory. In fact, these are the calculations which convinced me to enter this field. And if we think what people have done in 1980 or before, and what we are doing now, it's actually, I think actually we are still very much on the same track as people have done before you guys were born. So what Yin and Cohn have done in 1982, actually there was a paper in 1980, but there was a lot of mistakes in it. But anyway, so the PRB in 1982 shows the total energy of silicon as a function of volume. And you see this parabola type, which you have seen before. And you see this for different structures, for the diamond structure, for the hexagonal structure, for the beta-tin structure, simple qubit, PCC, HCP, and so on and so on. And they plotted it as a function of volume, and they used, in fact, the normalization, they used the experimental volume. So 1 is the experimental volume. And in 1982, they could say, this is the predicted structure, and you see they used the LDA. That was before, in fact, people had seen the Chapelier results. So in fact, what they used was actually the Wegener equation for the whole range. They used pseudopotentials and the electrorelativistic effects. And they said, actually, this is a structure. But then they also said, actually, if you would actually reduce the volume by external pressure, the system should undergo a phase transition to the beta-tin structure. And the common tangent between these two, this is this dashed line, the slope of this tangent tells you the pressure at which the phase transition should take. So that was in 1980 that people saw you can use, in fact, calculations to tell about stability of crystals, existence of crystals, pressure of phase transitions. There was another paper, in fact I was at IBM, so I was somewhat with these guys, by Moruzzi, Janak and Williams. Williams was really the key brain behind it. Unfortunately, or whatever, maybe actually he liked it, he got at some point a midlife crisis and wanted to do something different. But he was really a fantastic scientist. So I show you this as well in a moment. But I just, another part actually of this Ying and Cohn work. So basically what also came out from 1980 work is looking at the electron density, understanding that if it's germanium, it is somewhat has electron density in the middle, it's covalent. If it's gallium arsenide, the electron density is a little bit more to the arsenide, so it adds a little bit of an ionic component. If it's zinc selenide, it's really getting more and more ionic. Basically, having this part of the periodic table from germanium, gallium arsenide to zinc selenide, which you can all calculate it, even if you would not know this, you can calculate it and getting insight about the nature of chemical bonding. So on the other side, the other group was Moruzzi, Janak and Williams, and they actually looked at metals. So they looked at a very different thing, calculated electronic properties of metals, and they published this actually in a little book. So basically they had a book which has all the information they calculated. Again, they used actually the LDA. They didn't use pseudopotential, but a Buff-tin approximation, which means it assumes that the electron density can be approximated in every iteration as spherical around the nucleus, and again neglecting relativistic effects. And what they have done is all these materials. So to some extent you would say actually nowadays this is a high throughput type of screening thing, looking at all these materials, calculating the band structure, calculating even the Grüneisen, the electron phonon type of parameter, analyzing the bulk modulus. All this was done in 1978. And I think this is actually what I think is really a role model, and to some extent it's really amazing where we are now. We are following the same spirit as they have done many, many years ago. So you've seen that you can do phase transitions, right? So you have actually, you say actually this is at t equals 0, the stable system, and if t is not equal 0, actually this is a phase transition to a different type of structure. But in fact, what then also came, and I will be very fast because again this will be discussed in one of the lectures, it was developed what is called ab initio atomistic thermodynamics. This is a strange word in a sense that thermodynamics is phenomenological, but together with DFT you can really have an atomistic treatment in asking what is happening if the crystal is not really just by itself, but it's really in contact with the gas phase. What is happening if there is actually atoms coming from the gas phase which may actually absorb or which may actually change the system. Maybe actually iron and oxygen does not really like to be iron, it likes to be iron oxide. That means actually using an additional concept of thermodynamic equilibria and actually thermal reservoirs. And I think I guess Peter Kratzer will talk about it, or someone else will talk about it in the second week, in discussing really this concept, which really gives you also thermal equilibrium under realistic conditions, what really is what a surface or what a system really wants to assume. That gives us predictions about, if you don't know, what is the concentration of defects at finite temperature? How many defects will a system really have if you really keep it on a certain condition? What is the surface structure? What is the surface composition? We just said actually if something is in a gas phase of hydrogen or oxygen, how much actually will it change because oxygen will interact with the surface under realistic environments? You can look at order and disorder phase transitions, and you can look at really equilibrium shapes of nanostructures. You can say actually what is the shape of a quantum dot? All this can be calculated with these type of thermodynamic conditions. The limitations of all of this is the accuracy of the exchange correlation functional. For this, you need an accuracy with respect to the Boltzmann constant times temperature. Now this is a small number, and if you see that, you think actually you don't dare to do this because this small number you will not really achieve. But on the other hand, you are here actually what helps you is at the end you're looking at total energy differences. You want, in a phase transition, you want to understand this phase compared to a different phase with the same type of atoms. And so in this energy difference, in fact, a lot of these errors really cancel. And that's why this approach of ab initio atomistic thermodynamics was so successful. But still, this is only thermodynamic equilibrium. And a big part of this workshop will be telling and exploring that life is not static. Life is dynamic, right? And that means we have to do molecular dynamics. I have one old example, I think from Luca Giringelli. He talks about something different here, but this is actually looking at a small particle of gold at room temperature. Now the first thing, gold in this size, if you think actually gold is gold in terms of color, actually gold is red if it's small. But you also see actually this thing is really vibrating the whole time, and then it's jumping from one structure to this structure, and then it's vibrating for this structure, and then it's jumping to another one and vibrating for here, and then jumping to another structure. It really visits several structures. And if you want to understand the catalytic properties, what is actually good for catalytic properties, only one of these things which are visited over time need to be important. If you would stay, in fact, at the equilibrium geometry, you would not find anything. One of these which are visited in the dynamics is the most important thing, and so it's really important to understand or to appreciate life is dynamic. To understand what's happening, you have to go ab initio with density function theory forces to understand what structures are visited in reasonable timescales. This is my last example, which I also think is an extremely good example in how one should use density function theory. It's an example by Alfie, Gillen, and Price. So this is the Earth. What we know about the Earth is mainly really the first couple of 100 or 50 kilometers below the Earth's top, outside of the Earth. But actually we know a little bit about the structure. We know about the structure from earthquakes, actually also from some bombs, that reflection of a wave, and measure the reflection at some other place, and you measure phase factors and time differences. You know actually there are several parts of this Earth. There is an inner core, which is most likely solid, then there's an outer core, which is liquid, and then there is actually the mantle, and so on and so on. This is 6,000 kilometers. You know the pressure because you know actually the material, and basically the material on top is really creating the pressure. The question was, when we say this is liquid, and this is liquid probably 90% iron with a little bit of sulfur, selenium, carbon, and oxygen, what does liquid really mean? Or actually we know the pressure, but what is the temperature? How the hell can you get the temperature? Density function theory can tell you. And the idea is the following. The inner core, which is solid, and the outer core, which is liquid. This is a phase separation. So if you can calculate the solid-liquid phase separation curve, or you can also say the melting curve, right? You go from solid, this is the temperature, you heat it up, at this point the thing gets liquid. You calculate the melting curves as a function of pressure. Now, you can, to some extent, also measure it. You can measure with a diamond Anvent cell, you can measure some of these curves. You can also actually measure it, there are also 2 points here. So the diamond Anvent cell somewhat stops at 200 gigapascal, but you want actually to know the temperature not at 200 but at 330. So people have done this by an explosion. So in the millisecond of the explosion, if you can measure the temperature, you have the right pressure. And then of course the sample is destroyed. So there are somewhat ways, but with a big error bar. But you can calculate everything. You can calculate, so this line is a calculated melting curve of iron, going from solid to liquid. And that means at 329, here, going to this is the point, you go to here, and you're at 630 Kelvin. Basically, knowing the pressure and knowing the melting curve, you know the temperature at this point. So this is what you should do. Think about a question and then really think how to use a calculation which was not made for calculating a temperature, but use it actually in a clever way to really contribute to get a better understanding. And then of course they also could say, if I look at a system which is liquid at this temperature and this pressure, they could look what is viscosity, how liquid is it really? It is basically liquid that it has some turbulences, it really can flow, and that actually plays a big role for how the magnetic field on the Earth is created and so on. So this is actually how methods should be used. And with this, I'm basically at my last 2 slides. I think the field has seen significant progress since the fantastic early work by Marvin Cohn, who is actually an emeritus professor in Berkeley, and Art Williams and his crew. But the knowledge that we have is still very close to zero. We want to contribute to material science and engineering, but if we see what we know that there are 240,000 inorganic compounds that have been synthesized. But actually, it's also clear there must be many, many more materials which are possible if you really think what you can combine with different materials. But what do we know about these 240,000? From these 240,000, from only 200 compounds, we know the elastic constants. For only, say, 300 or 400, we know the dielectric constant. Heat conductivity for 200. Superconductors for something like 1,000. And then a very important popular field is topological insulators. In 3Ds, there are just 42 known. In 2Ds, 7. There are many, many more which are possible. And so getting an idea about structures and patterns in all these elements or materials would be really the next thing to do. So far, for almost everything, we are well below 1% in coverage. Actually, probably well below 0.1% in coverage. a lot of things to find new structures, new materials with probably much better properties than what we are using and knowing today. And that brings me really to my conclusion. I think we hope that you really learn the power and the limits of computational science, but you also get an idea what I call the fourth paradigm, the big data-driven science. I think you want to actually know about the future, because actually this is where you will actually be all your life from now on. But knowing actually the future, it's already there. I mean, you just have to see where it is. At several places on the planet, it's already existing, and you just actually have to be and pick the right thing, and then you are there. Thank you very much.
We have time for a few questions. Is there one? Okay.
Is there any alternative to Warner-Heimer approximation? We don't, let's say, accept it from the beginning. You mentioned that for some phenomena, Warner-Heimer is not fully satisfying the equations. Are there any alternatives to that?
There are alternatives which are worked on, but actually there is no practical solution yet. So that is a field which I think, I mean, the first thing is you have to realize that this is important, right? And you realize that, for example, if you look at band gap in semiconductors, you see that the temperature dependent of the band gap, that there is actually something like 0.1, 0.2, maybe 0.3 electrons actually not really accounted for. If you try to understand electrical conductivity, actually which is finite, and it's finite because of electron-phonon interactions. So you know actually where it plays a role. We have a lot of ideas how to do this, but we don't have a practical treatment and things programmed yet. This is something where you will become famous if you do it. But I have to say, actually, several people are doing it. I see one face at the very end. So Hardy Gross is actually talking tomorrow about the density function theory. So Hardy has actually done a lot of work in electron-phonon coupling, general theory. Making it really to a practical material science problem is still a lot of work to do. I mean, Claudia Draxel, who is really the professor at the university and in physics, is working on it. We are working on it. So several people are working on it, but I don't think we have actually a good solution yet. But the first thing to realize in science is really identifying the open problem. Then you need time to solve it.